All right, here we are for day 10 of Advent of Code 2023. Today's puzzle is titled Pipe Maze, and strap in because this one is a big one. So for today's puzzle, here is a sample of the cleaned up input for day 10. The full stops in this puzzle are dirt or background and can pretty much be ignored. The other characters are either pipes or the start location, which is labeled with an S. The pipes roughly form the shapes of what they are. There's the vertical pipe, the horizontal pipe, and the four corner pipes. Although here we can only see three of the corners because the S is covering the other one. Our job for part one is to trace a path along all of the connected pipes and figure out the furthest possible distance you can get from the starting point in terms of steps through the pipe. So if we take that original sample map, but we replace the symbols with a value of how far they are from that S position, the starting position, you can see that if we start at S, travel in two directions, increasing the distance as we go, we move around the pipe, the furthest we can get in this case is 4 steps. And if this was the input for our puzzle for real, the answer would have been 4. Now, here's a slightly different look at the same distance, and this is going to become important when we look at the solution we implemented. This time, rather than traveling in both directions, we pick one direction and say that's forward, and we keep traveling forward, following the pipe as we go, until we end up back at the start point. And then to get the answer for the distance, which again should be 4, we take the total distance, we divide it by 2, and we round it up if it happens to be an odd number. In this case, 7 is the length before we end up back at our start position. So 7 divided by 2 is 3.5, and this gives us 4 as our rounded number. Now, initially when I was doing part 1 of this puzzle, I implemented the first method. After implementing part 2, it switched over to this one. So it's important to see both in this context. Now, our actual puzzle, the input that we get is a massive version of this file, and notably, it's not as clean as the examples given here. There's not as many background tiles. There's a whole bunch of disconnected pipes littered around the map, and part of our challenge is determining which directions, based on where we are valid movements based on the pipes surrounding us and the current pipe that we're in. Now, to do this, we consider each of the pipes and note that for any of them, regardless if they're straight or if they're bent, they only have 2 entry points. If we're currently in one of the 2 entry points of the pipe that we're considering moving to, we can move there. If not, that's not a valid direction to move to right now. That doesn't mean that pipe isn't part of the loop, but it's just not the next step based on where we're currently sitting. In our method that we described before, we trace the whole route traveling in one direction. This means when we're checking where to go next, we only check 3 out of the 4 possible directions because we don't go back the way that we came. And this ensures that we don't end up running around in circles. Now let's have a look at the code for this puzzle. As always, if you want to see the full solution to today's puzzle or any of them up to day 18 where I stopped, there's a linked GitHub repository down below. All right, starting with something easy here, we define a enum called tile. This has 1 entry in it for each of the different pipes. It has 1 entry for the start position, which in the context of the story for this is called the animal, and 1 entry for dirt, which is the background. While this is not strictly necessary, we could just match on the characters. This is helpful for concrete type matching, which we'll see a little bit later on. And yeah, that's about all there is for this enum. Next thing we define is a tile state enum to keep track of the state of each of the different squares in the map as we traverse it. There is a left state here, which is used for part 2. For right now, just ignore this. It'll come back into context with part 2. We also, for the sake of making debugging a little easier, implement the debug trait for the tile state enum, which means that when we print it using the print macro with the debug characters, it just prints a single character, which makes it a little easier to visualize against the maps. Two more data structures here. We define a struct and an enum to help us in navigating through the grid, which is the map. Position stores a row and a column, just two values there. And cardinal is an enum for the 4 cardinal directions, north, east, south, and west. And for the purposes of this puzzle, north is up. We then start with a simple function to determine the opposite of each cardinal direction. This helps in a few places later on. It should be pretty self-explanatory. If you've seen a compass before, you know what the opposite of each of those is. So we take it in and give the opposite back. Next, we create a small parsing function which maps a character to a tile. There is a case in here for the none scenario right down the bottom there. But given the input is well formed, we actually never get a character other than any of these, so we don't actually ever end up in that state. The next helper function we have allows us to take two positions, those two position structures, and return the relative direction between them. So this assumes that we're at the point here P1, and we want to know which direction P2 is. The none case exists here in this match because technically we could put P1 and P2 anywhere in the map. We don't, so it's not really that useful. But for completeness, it does need to be in here because we get an optional as the final result. So you can see here, depending on the difference in rows and columns, and remembering that we are working in row column format here, south is one row higher, east is one column higher, and so on. And based on the difference in row and column values, we can return the right direction. Next, we add a function that returns true if the tile that we're testing accepts an input from the given direction. So you'll start to see how those two functions, this one and the one before, work together. For example, here, our vertical pipe, it accepts input from the north and the south. The animal, our starting position, accepts input from any side because we technically don't know what kind of pipe is underneath there. There should be a pipe at the starting point, and there is, that only has two inputs, but we don't know what it is. Working out what it is doesn't help us solve the problem, so we just implement this special case that says, regardless of the direction, you can move to the start. Now diving into the main function for day 10's code. As usual, with most of these, we read the contents of the input file into a string ready for parsing. And to store the map here, which is the collection of tiles, we use a vector of vectors. So it's a two-dimensional array of the tile structures. We also initialize a few placeholder variables, which we will use to trace our way through the pipe. Left's head is used for part 2. We can ignore it for now, but again, it's just a vector of positions. And to make part 2 easier, we also put a ring of extra tiles around the map that we're provided. This is useful because for part 2, we need to check the surrounding area and we want to pick a start position. And by adding that extra row of padding, as you can see in that last line there, we can pick a position without any risk that the position we pick is part of the pipe. And this is a pretty common pattern when dealing with algorithms that run over maps or 2D arrays, to add that extra padding to give yourself some guarantees about the outside. Now looking at our parsing loop, it's pretty simple. We read in each line from the file, which creates a new placeholder vector called current row. To do our left-right padding, we add a single dirt tile to the start and start parsing the input for that row. Read the characters one by one. We then use the parse tile function that we defined earlier. We push the tiles into the vector, taking special note if we happen to find the start point, that S character. If we do find that, we store that in the animal variable and we push that start position into the vector called head. Finally, we add another dirt tile to the right to complete our padding and we move on to our next row. And then once we've made our way through every row in the file, we add another empty vector at this point for more padding from the top and the bottom of the map. Now that we've finished parsing, we add 2 for the extra padding and 1 because we start counting at 0 to the number of columns and number of rows, which we use in future parts of the code. We also fill in that top and bottom padding now that we know how wide the map was. When we first started parsing, we didn't know, so we just put empty placeholders in there at that stage. Next, we create a empty map of the same size as our actual map to store the distances. So that's the counting variable of the distance around the loop. We also create another 2D vector for the state of the tiles to keep track of whether we've visited them before. And we populate both of those with, in the case of distances, we put in the value -1 to be our placeholder for not a sensible distance. And for the states, we push in the unvisited state for all of them. Once we've initialized those 2 vectors, we set the start position to have a distance of 0 and a state to say that it's in the loop, which means it's considered part of the pipe. Next, we start running through a basic pathfinding loop. We continue to loop until we run out of places to go, which is when our head is empty. We take our current position and check all of the 4 surrounding possible directions. So that's north, east, south, and west from where we're currently sitting. If any of those positions are off the edge of the map, then we just skip them. Otherwise, we get the tile type of the current and the candidate tile ready to check if we're able to move into that tile. Following this function down a bit further, once we have those 2 tiles, we can check that moving from where we are into the target tile is valid. For that to be true, our current tile needs to allow movement in the opposite direction to where we want to go, and the tile we're targeting needs to accept in the direction we want to travel. Now, if both of these are true, we then do a check to say, hey, have we been to this tile before? If we've never visited before, we note the distance, number of steps it took to get there, and put the new tile that we just moved to into our head of next moves. Now, technically speaking, and you might have picked up on this, you might be thinking, why do we use a vector for the head variable here if it only ever has 1 or 0 elements in it? That is a very fair question. This could have easily been an option type after implementing part 2, but based on the travel in both directions setup, we needed a vector. And the default for a lot of these pathfinding algorithms is create a vector or a list to store the candidate places to check for movement on. And you'll see that a little bit later on. So once we've exhausted all the possible positions that we need to check, so we've run out of new locations we can go, meaning we must be back at the start, we need to find the highest value of distance in our map. Because I originally implemented the search in both directions, this checks the entire map for the largest stored value. But in this case, we could have easily just kept the largest value that we've ever recorded and just divided by 2. But this is a bit of a hangover from that previous implementation. Either way, we grab that value, we divide it by 2, and that's our answer for part 1. In this case, 7,097 steps is the furthest distance you can be from the start. All right, let's dive into part 2. So part 2 is a little bit odd. They provide us with this similar feeling pipe maze. It's an example input. It's still a loop of pipes connected together as it was before. And we could easily repeat our part 1 solution on this code. But to solve part 2, we're after something slightly different. Now here's a different view of the same map. The difference here being there's the extra annotation of the zeros and the I's. So the zeros, or the O's, are part of the map that is near the pipe that is reachable. So if you start from somewhere outside this pipe network and you start moving around all of those empty dirt spaces, you can reach within the pipe area all of those places marked 0. You can reach all those dirt places around the edge as well. Where you can't reach, though, just by traveling through the pipe, because the pipe, in this case, blocks our movement, is any of those areas marked with an I. So our job now is to find the total number of unreachable tiles in our much, much larger map. Before we do that, though, there is one more slight caveat that we need to consider. So this is a slightly different version of that previous map with one less column running through the middle. You'll notice this time, though, that those tiles in the middle are still marked with a 0 to say that it is reachable. This is because the rules of the puzzle say that you're allowed to squeeze through parallel running pipes. So that JL, the 2 vertical pipes, and the 7F, your character, your player, however you want to think about it, is allowed to move between those 2 pipes. You can't move through a vertical pipe moving east or west, and similar with the others, but you can squeeze through. Now, this makes our process a little bit more difficult because we know we can't necessarily reach all of these locations just by traversing the map. But there is a nice, easy to understand solution that is slightly inspired from a screensaver all the way back in Windows 95. So, you may or may not be old enough to have seen this screensaver in Windows 95. I think it was in Windows 98 as well. If you haven't, it was the computer trying to solve a maze by moving through the level. Now, the way it moved was fairly simple. When I first saw it, I thought it was random. I was a kid, but then later realized that it had a pattern, and that pattern was follow the left wall. So if there was ever an opportunity for the computer to turn left and follow that left wall, it did. Sometimes this was immensely frustrating because you could see the exit of the maze right in front of you, but there was a left turn coming up, and you knew that the computer was going to turn left. But following this method, always turning left when you have an opportunity, or I guess in terms of a physical maze, you might think about putting your hand out on the left wall and dragging it along. You're guaranteed to eventually find the exit in these kind of mazes. So if you ever get stuck in a real maze, this might be a handy thing to know. But we digress. Applying this idea to the puzzle, here's the approach I came up with. First, move along the pipe as you did before. Move in only one direction. As you move, mark the tiles that appeared to your left. So if you've never seen it before, it's marked as left. If we later end up visiting that tile by it becoming part of the pipe, we then include it in our loop. But if not, it just gets the left marker. Now, once we've done this after traversing the entire pipe, we then apply a flood fill to expand anything that's marked as left to anything that those left tiles can then reach, and so on and so on and so on until we run out of target tiles. And then anything that hasn't been marked as either part of the loop or one of the left tiles is unvisitable. And summing the number of unvisited tiles will give us our answer. This works because I implemented it and got the correct answer, so let's have a look at the code. To help with this, we define an extra helper function. This function takes a tile and a direction that you're about to travel, and it says which tiles or which positions relative to where I am should I consider to be on my left. Now, for a straight path, so that is the north-south or the east-west tiles, there's only ever one to your left. For north-south, if you're moving north, it's the one to your left, or I guess to the west in terms of maintaining cardinal direction. If you're south, it's the one to the east, and so on. If you're moving around a bend, we consider 2 tiles to be to your left, and that depends on which of the 4 bends that you're going around. But you can see there that it either returns 1 or 2 new positions that we need to check. Coming back to our parsing loop, you may have noticed this one before. We added some code to account for part 2. When we arrive at a new position in our loop traversal, we then also check all of the left-hand tiles for that given movement. And if we've never visited them before and they're a valid tile within the map, we mark them as left and add them to a collection of tiles that we're going to expand on later, which is this vector left's head. Once we've finished that parsing, we have a bunch of tiles that are part of the loop and a whole bunch of tiles that are part of the left side, and then some unvisited tiles. And what we do is we continue to work through that loop of left tiles until it becomes empty. We grab the tile off the list. If the tile is no longer a left tile because we visited it as part of the pipe, we just continue, we skip it. Otherwise, we check the 4 surrounding directions to that left tile. If any of those tiles are unvisited, we mark that as left as well, so connected to a left area, and we add that to the list of tiles that we need to check. Once we've finished with this loop, we will have maximally expanded our left's area, and every tile in the map will either be marked as left, part of the loop, or unvisited. Now that all that's done, we sum up the total of the tiles marked left and the tiles marked unvisited, and we report both totals. The reason we report both is that there's no guarantee that picking left was the correct choice here. If we had a pipe that looped in a slightly different direction, we may have marked the unreachable tiles as left and all of the ones that were reachable as unvisited. So in this case, we just print out both, we have a look at the numbers, and 355 was the correct answer, so that's the one we reported. And with that, we're done with part 2. This was definitely one of the more complicated puzzles in the first batch of days in the Advent calendar, but hopefully this video helped you understand how to get a solution. If it did, please consider liking, subscribing, all that good YouTube stuff. And in either case, until next time, I'm Elliot and I build stuff.